thanks. So let me just continue. So today I don't know, there's quite a lot I want to say because this is like the 2/3. After this talk is going to be 2/3 of my lecture series, but I hope to cover 1/3 of what I want to talk. And also there will be like this difference between unico, quasico will also appear today. So maybe I add a lot of confusions. So we will see. So recall that the proposition, the general proposition we're going to use is just write it down again one time. This is in VR under some condition of certain morphisms. Assume, and also some then we'll get the following thing. Give us a way to compute the trace of Y-geometric method, Y-geometric correspondences. This may just write the Harshal homology of, let me write this is A, this is F, so this. And in this case, the whole point is the bottom line is fully faithful with and admits continuous right adjoint. And I hope you at least see why such existence of continuous right adjoint is important thing. And the other thing is this is get one, and the second I didn't mention in the lecture, but in the Q&A session is this the convolution also admits a bilinear right adjoint. Okay. So this is what was said yesterday, the general thing, and we are going to apply this to the spectral side today. One more thing I want to mention is the particular case today is again the situation we're going to use is Z is given just Y, go to Y times Y by two morphisms. One is identity, the other is some automorphism. In this case, I think in also like this this F is actually just A. With like bimodule structure side change, like the right action of A is just multiplication, left action of A is you first like apply phi and then multiplying it, okay? And in this case, there's I think also, as Arnold mentioned yesterday, there's inside here, there's this particular map, you have this X go to, because this is like in this form, one tensor X. So then this, in particular, this element or object will go to here is just given by, in this case, this is like this twisted loop space. This is D of X times X over Z. So we get this one tensor X will be under this embedding, maybe it's will be just this guy of X. Okay. A particular case is if X is Oh, maybe let me not write the X. Maybe change the notation to A, little a. The particular case is for A itself is a unit of this monadal category. It's a kind of this because then the claim is actually one can show is the following. So this is a lemma. I leave it to you to check. It's just diagram tracing. Is Q plus of 1 of A. So recall this is actually the unit is given by the following thing. It's a push forward, really push forward of the unit, or maybe write it in this way. Sorry. Write it in pi x upper star delta. Okay. This is in dx times x over y, and then the lemma is this is actually the following push forward. You do loop space of x, go to loop space of y, then push forward of the constant like this lambda of x, which is just pi lambda coefficient. Okay. So this is the particular example I was is when this x is b plus I, bi plus y is this is a situation we mentioned last time. Apply this, then what you get this what you get this unit of A is just the standard or co-standard object on the unit strata, maybe some monodromic object in shifts of I plus I or I. So it's kind of just the torus monodromic shift on here. And then what you get is this particular case, 1A, is just I of 1. Star or shriek doesn't matter, maybe write shriek, of compact induction from the Propi-Iwahori of G of F of constant. Okay, so you can check this is so on the this particular you get some particular concrete some object like the compact induction from the Propi-Iwahori lands in the image at least. All right, okay, so now I want to apply this to, by the way, where can I see the time? There's no, oh, okay, that's fine, maybe I put the iPad. Okay, thank you. All right, thanks. So now we move to the spectral side. The spectral side. Maybe, oh yeah, I think we need to go to the, and then I will take x to be the Tame Langlands parameter, but with valued in the Borel. So let me, for simplicity, assume G is split. It's okay for at least Tamely ramified this computation, but let's just assume it's split over GF brave. Just I'm considering parameter just from the Galois group of F brave. I mean the completion of maximum unramified extension to B hat. So this is once you choose a generator, it's just do B hat complete along semi-simple points, the mod B hat, Okay, so this is B hat. It sits inside the B hat. You go to T hat, and you complete basically along all the close points that are prime to P or something like that. Then Y will be take. So this is really you think about the form, either like an in edge break stack or something like that, or formal edge break stack. This is like some G hat, modular G hat. Okay, we want to apply this, but then the fiber product is usually called like some Steinberg, some version of Steinberg, some Tame version of Steinberg, and this is after choosing Tame generator. Look at this. All right, and then over here I have phi. The action of phi from Y to Y is actually reason it's given by this map from G hat to G hat, go to G to its Q's power. This is a map we're gonna use, and this is not an automorphism of G hat, but when you restrict to this G hat complete, actually it's kind of an automorphism. Yeah. Okay. It's a. All right, and then what we want to apply this is some shift theories. Now this is the first confusing thing is I want to apply to the theory of incoherent shifts, but this incoherent shift is not exactly as what Lucas was talking about on Monday. But let me first write it down and then just make a comment. So this is there's apply 2. This is kind of maybe the first confusion of the lectures. To the following thing, there's actually theory of incoherent shift from the correspondences of int edge break stack over lambda. Lambda is regular Noetherian, like a finite, let's say, over 0 or FL or QL, FL bar, QL bars, and take almost a finite presentation, which was mentioned, I think, before, and then morphism, which type of morphism I allow to push forward. Those are int finite, almost finite presented morphisms, and what kind of morphism I allow to pull back arbitrary morphisms, and then the push and and it goes as follows. So this will send you'll get this G upper shriek, inco upper shriek. So this is F lower star inco of from inco of Y to inco of X. Okay, so that's some theory, but this is not what is this inco? Inco of X is defined as incompletion of the coherent shift of X. So this is really the first thing is, and this is in general, not, there is always a functor, but in general not equal to what Lucas called the inco on Monday, and I will use, because of this, I use another notation called the QC upper shriek. This is what like Benzvey Netherlands used notation, also in their joint paper with Devi.
In our paper, we actually write ICO, which fortunately is also different.
We
write ICO.
ICO. Yeah. Okay. So this is ICO, this one. Oops. That's good. So at least there's no clash of notations. All right. So this is really. So this is basically this. The differences. They are really they are the same for schemes or edge break spaces, but different for stacks. That's really the difference where it comes from, and this doesn't satisfy F descent.
Also, over characteristic 0 fields, they're the same in logic.
Yeah, in general, I would comment that. General. And they are the same. Yeah, but another remark is for what's called the QCA stacks over Q. This is equivalence. They are the same. And it's just happens, I think, like, because I also want to work with modular coefficient, and it just happens in the modular coefficient case, it seems to be incompletion of coherent shift is more correct thing to consider rather than just this distant thing. So maybe give an example for those, you know it, but I think there are people probably not quite familiar with this stuff. So let's just take an example. Is X take the classifying stack of B mu L over FL. Okay, so let's see what's the difference between these two. In this case, this one is defined by descent. So it's basically, it's still, actually, it is the same as quasi-coherent shift on, this is actually a smooth stack, so it's the same as a quasi-coherent shift on this stack, and concretely, this is just the module, it's basically a representation of this algebraic groups. So it's a module over the group ring, which you can write as Ft, T minus 1 to the L modules. Okay? But what is this coherent X? Is actually just a coherent shift on this spec of this ring. But the whole point is because this is not a regular ring, so it's a singular ring. So in completion of coherent of X, this map to here, this is what something like the Psy wrote in previous talk, but this is not equivalence. Okay. Because this is basically incompletion of perfect thing, this perf. The whole point is perf and the coherent shift are different in this city. All right, is there any question about this? Okay, so anyway, there's such shift theory, and you can apply it, and then the point is this is with respect to this shift theory, this F, so yes.
Do you mean V of Z mod LZ, the constant coefficient? Because then you get modules of the Cartier dual, which is
Okay, let's do yes. Let's okay. Yeah, multiplicative group. Yeah, it's bit. Yeah, you're completely right. Okay. No, that here is what I'm writing is a group algebra. Yeah. For me, then it's a fun. Okay, this denotes a group algebra. Yeah. Okay. But it is this one anyway. It's this one. All right. So that's the difference. But anyway, there's also such formalism, and proposition is applicable in this case. So you have to trust me, but there's no way to see why this is true. But more or less, it's because this X to Y, this map is a kind of proper map, and the diagonal is like quasi-smooth morphism, LCI morphism. So it's still applicable, and there's some argument in particular in also to show like the tensor product. Is equivalence, but that's fine. So therefore, we get the Hochschild homology of Inco of the Steinberg with this twist, the one twisted by this endomorphism or automorphism. This maps fully faithfully into here. This LG. And it turns out, what is this? And this is, on this, you can recall this is like, by definition, I mean, I think this was more or less, if this identity was mentioned yeah, even in general, I think it's more or less the same as what mentioned in David's talk. So this is what I call just Tame parameters. Okay, so this is a general thing, and then again, it's this is you will need to identify the image. So let me. It turns out, unfortunately, in general, we still don't have a good. Couldn't see exactly what the image is. So let me tell you what we know, at least what I know. The first one. So let me just write this as a HH to instead of write the whole thing. So first one is HH. It's a full subcategory of a category of incoherent shifts on the stack of Tame parameters. And on here, there's the action of imperf act on here. Just so this is so for stacks in positive characteristic, again, there's a difference between imperf and the quasi-coherent shift, because actually quasi-coherent category of quasi-coherent shift in general not compactly generated, and it turns out it's better to work with imperf rather than quasi-co. But for characteristic zero coefficient, it doesn't really matter. It's just the quasi-co. Okay. So, and this is it's actually stable under the imperf action. Let's say at least that when L does not divide, let's say pi, it's like some condition like L does not divide the order of a torsion part of pi 1 G hat. If it divides, you can replace this by something slightly different. It's still okay, but let's not worry about that. This is again, it's let's just see in this way. The second is if the derived group is simply connected, or if, let's see, the order of the Weil group of G is invertible in lambda, for example, case of characteristic zero coefficient, then what something is containing, you can see this contains large image. So you can consider all the spectral Eisenstein series of imperf from the all possible levy. This will be contained in HH. Okay. So in particular, it contains the imperf itself, and but also all possible levy. And of course, the third is when lambda is rational and the G arbitrary. No restriction. Yeah. Let's just write this. Then, oh yeah, maybe before saying that, let me go a little bit further. 2, but this 3. This 2 is part 2 is actually HH is contained in inco of Tame, G hat F, but with certain so-called the unipotent singular support condition. This condition does not really show up, for example, in characteristic 0 case, so it doesn't really show up in the talk like this the other series, but for modular code, for example, in characteristic P, this is really condition it will show up, and we'll see there's really some funny thing happen. This basically gives the second part gives an upper bound of what's the image. The third part gives a lower bound of the image, and when lambda's QL coefficient is upper bound and lower bound are the same, so it's just like, and maybe I just write SH is just this inco of everything. And this is very close to this theorem of Benz-Van-Naden and like talk some slight variant, maybe it's a slight variant. But it's more or less the same thing.
Is there any kind of guess for what HH should be? Like how to describe this?
I think it should be just the whole inco NILP, but unfortunately, I don't know how to prove it at the moment. But at least it contains many things. It already contains all the imperf and anything come from the Eisenstein series. So I think that's.
So do you expect that the lower bound and the upper bound?
That's actually a question for audiences. Yeah, the both proof in characteristic 0 uses the singular control of the essential image of proper push forward using singular support by Arinkin Gates grid. There's some theorem, but simply that theorem is false in the positive characteristic. So you can't use that singular support condition to control what is the image, what you can get. So, yeah. So maybe let me just sketch the proof of the second part. Of 2. Okay, so to see that it contains, for example, let me just say, sorry, not 2. 2 is actually, again, come from, remember, singular support. So, I mean, okay, there is also still theory of singular support for coherent shifting positive characteristic. It gives you some control of pull-push, but it's not really something. It says that the image is contained, for example, pull-push, the image will be contained in some subcategory characterized by singular support condition, but it doesn't really, I mean, it may not be always full image may not be full subcategory characterized by those singular support conditions. So it's just simply false, so that's statement. So that's, so anyway, so part 2 is not really different from proof in characteristic 0. Part 3, so let me just give you some idea how this is done. So, so actually we need to understand the following thing. We have this, recall this is by definition, not by definition, by the proposition, we said the image of this the trace does come from this Fourier cycle transform. And in this particular case, actually, I call it like the so-called spectral linguistic induction. Because in this case, this space, let me denote by tilde. What does this classifies? So this is just a space of parameters, Tame parameters. And what does this one classifies? So this one, maybe write it here. This classifies those phi just as WF2 G hat, and also P a Borel. Maybe write P hat a Borel of G hat, such that phi of the inertia is contained in P. Okay, just because in this is Tame situation, the whole inertia is basically generated by one element. Is
this all modulo G hat conjugation?
Yeah, everything then is modulo the G hat conjugation. Simultaneous conjugation. So here also it is. Yeah.
It's like some Fourier resolution of the initial conditions.
It's exactly. It's just so, and this map actually is surjective map, proper surjective, and depends on what's the image of the inertia. It's if the inertia is completely trivial, you have the whole flag variety. If the inertia, for example, is a regular unipotent element, you just have one flag variety. You have just one Borel content in it. Yeah, and this map Steinberg the delta will send this maybe right in here. Delta will send the phi and the p to what? What's Steinberg? Steinberg, I think there was some interpretation. Concretely, would be that element in the group and the two Borels containing that element, and then this element will be just a phi of this inertia. And one Borel is this, and another Borel is a phi of Frobenius applied to it. Sorry.
You want the Tame generator?
Yeah. Tame, yeah, if we fix the generator, let's yeah. Tame generator. And then you have phi of Frobenius act on P hat. Okay, that gives you another Borel, and both contain the phi of Tame generator. So this is I mean, before it was just a manipulated symbol, but this now if you plug in the stacks, we get some concrete. So it has this has some very nice geometry, just a lot of geometry. Just like, because now you can look at the Borel and you apply Frobenius to it, the Borel, relative position of Borel, so you have a lot stratification, you have some line bundles, so there's a really fruitful geometry on it. Okay, so this doesn't, but how to prove it, part 3. So what actually, because this whole category image of the Hochschild homology is stable under the action of imperf, what I need to show is just need to show the structure shift O is contained in the image. Okay? So, but then this, what we will do is, you can consider, recall this map is conference base change from X to Y. Okay? This is base change. And the X to Y is the usual Springer, Grothendieck-Springer map. Is the Grothendieck-Springer map. And so, by the way, the delta, this map itself is base change from x go to diagonal of x. So itself is a LCI map, and its upper shrink and upper star are the same. Okay? So you see that, therefore, you see this delta up inco upper shrink of O, then apply, this is Q lower star inco is just the pool. If I denote this is by pi, this is by what is this map? The given name H. Let's see. So this will be just a pullback of pi lower star of O. I mean, and the upper star. Okay? All right, but now we know that according to the classical theory of Gaussian-Springer resolution, the push forward of, like this is like a G tilde mod G, go to G mod G, and this push forward G tilde is just OG, tensor with, maybe everything is hat, sorry. There's a hat everywhere. Tensor with O of T hat mod W of O of T hat. Okay, so there are two situations. If the derived group is simply connected, then OT hat is actually free module over OT hat mod W, so it's basically a bunch of copies. So the structure shift appears as a direct summand. Or if order of Weil group is invertible, so this guy is also a direct summand of. So you just really need this. This is a direct summand under assumption. Of O T hat. So therefore, O itself appears as a direct summand of the image, so that itself lands in the essential image. And using the linearity under the action of imperf, you get the whole imperf sits inside there. And then one thing I did not tell you is this, actually this Horry-cycle transform is also compatible with the spectral Eisenstein series construction. So this is something you can show without too much difficulty, so that also contains all the image of spectral Eisenstein series of imperf. Okay. So that's a sketch of the proof. Any questions? Good. All right, so now if you combine, now recall this, now we compute basically the trace of both sides. One is automorphic side, one is a spectral side, and now we give this input of this is the Bezukov-Nikolov equivalence. Nikolov equivalence. Okay. So for this, let me assume, let's fix G is quasi-split. Fix unramified, sorry, at the moment. I think many things can be lifted soon, but it's unramified. So I just said, this shows that the O itself appears in the HH. Because of this equality, O it appears now. O of y appears. This is O of x. O of y sits inside as a direct summand. So therefore, its pullback will give you O of. Okay. Yeah. So you get O, and then you get everything. Yeah. And the fix pinning and also some additive character. So then there is equivalence, and let's see if for the lambda is either QL bar or FL with L bigger than maybe Coxeter number or something like that. There's some restriction of this. Then what you get is equivalence from the monodromic sheaf in code on the Steinberg. Tame. And for example, unfortunately, as just stated, it's not literally written down in literature of this. But let me just indicate what's there. If F is eco-characteristic, then of course the original work of Bezukov-Nikov, this is for lambda's QL bar coefficient, and then the Bezukov-Nikov ratio of FL bar coefficient, but in the unipotent case version. And then there's work using some work I did by Dylan, Yaowing, Zhiwei Yun, and myself. This could be to extend to a monodromic situation. And also there's this argument of Dylan and Jeremy Taylor in this Beatty situation. Then there's
Sorry, the four-letter acronym?
Huh?
The four-letter acronym, can you say again who this is?
This is Gabir Dylan, Yaowing Li, Zhiwei Yun, and myself.
Okay.
Yeah.
Sorry, does this exist as a public figure?
There's this endoscopy equivalence, reduce everything to unipotent thing. And this actually the spectral side reducing is, yeah, it's not written, but that part is much easier. And then you get, so you get some equivalence. Whether this is, I would say this is not the best way to do it. There will be better way to do it coming up very soon, I think. But at least there's such thing.
By monodromic, you mean non-unipotent?
Non-unipotent, yeah. Yeah. Then there's if F is a mixed characteristic. So far, the proof is translate the result from the equal to mixed. So this is the work of Bundle. Then there's also the work by Zhiwei Yun and myself, tells you how to translate the get the equivalence between F and head category in mixed characteristic and F head category in equal characteristic. And of course, there's a direct approach. This is by Anshas, Laurentko, Zhiyou Wu, and Jizhe Yu. So they at least construct the central sheaf in this situation, unipotent central sheaf. So they didn't give the full proof yet, but anyway. So there is such statement. As I said, this is maybe not the best one, but maybe the better proof will come out soon, hopefully by Xinyu Li, who gave a talk last week, and Jia Haolin. So coming out soon. Okay, so. Yeah, it will work in both cases, and I would say in this current version, what I written down using combine all different results, there's still one thing one need to do is compatibility of central sheaf in equal and mixed characteristic. But for them, they just directly prove everything, so there's no need to worry anything about it. Okay, so But and also this equivalence is sort of compatible with, I think last week Xinwen talked about this Bezukov-Nikov equivalence has a bunch of compatibility. For example, compatible with Frobenius action on one side, and also this maybe write as phi action on the other side, compatible with the action of outer automorphisms. Like for example, once you know this compatibility with outer automorphism, then you can also that's how you get the not necessarily just split group by like quasi-split group you can do, yeah, not just so. And there's a bunch of other compatibility. I think he listed a bunch of them. I can't remember, but there are at least some of them. All right, so if you put them all of them together, now you get the theorem. Is you get this Tame one. You compute the trace of both sides, and because these two categories are equivalent as monoidal category. Okay, this is important. This is equivalent as a monoidal category. Then you compute the trace. One side that we mentioned in last two lectures is just to give you a shift Tame on ISOC. The other is just this inco nup on look. And now we get at least the fully faithful embedding, which because it meets continuous right adjoint, so it sends compact to compact. Okay, and this is equivalence. If lambda is Q or bar, at least. Okay? And also, like Newton singular support condition can be dropped in this case. All right. So that's let's at least give like sort of the first topic I was going to talk. I mean, in the first day I list a bunch of topics, and this is the first one. So you do get some version of categorical local Langlands for the Tame situation. Okay, let me just say some consequence and recall this because this is also compatible with this universal trace map. Here you have this shift some monodromic on I plus LG. This goes the delta upper shrink Q. In this case, it's written as, I think this is written as Newton North star. This is equivalent. I mean, this is equivalence is compatible with this map, right? This is like a okay, maybe let me drop the
Like the full Tame version, like not just the unipotent part. With modular coefficients, is that actually in the literature?
I didn't write in my original article. I just wrote unipotent, but it's big. I mean, the computation is.
Yeah, I just want to make it clear.
Yeah. I mean, this equivalence is actually compatible with this map. Okay, and in particular, because this is a monoidal category, it will map unit, and the unit will match to each other under this situation. So then we can look at under this functors what the unit goes, right? On the automorphic side, we already see this unit will go to I1 from the basic Newton strata of compact induction from the I plus to G of F of lambda. Okay. On the spectral side, using this little where is it? Using this little lemma, I said it's actually come from this push forward of the loop group. So this is will be identified with this coherent Springer shift. What's the notation? S?
Yeah, S1J.
Huh?
S1J.
S1. But let me help you to use S Tame because this is. So this is just the pi from this log of Tame of B hat to O of log of B hat. So that is a match to each other under this equivalence. Just a direct consequence. And then corollary is you give, from here one gets kind of I mean, same spirit, but logically different proof of this result of Benzway, Chen, Tame, and Nader. This is the endomorphism of this coherent Springer shift is just the affine Hecke algebra, the Iwahori pro-P Iwahori Hecke algebra. So this is, I mean, the actual logical proof is different, but it's kind of same spirit using the trace construction. So now, maybe in the remaining couple minutes, let me try to confuse you by saying the questions, what is the image? If now I do not want to do the induction from the pro-P Iwahori, but just actual induction from the Iwahori under in co of Tame. Okay, so what is the image of this one? Now let's try to answer. This comes from all this confusing point of. Now this is actually this pro P1 tensor with the group algebra of this finite torus, and the tensor with the trivial one. Okay, maybe it derived tensor. Let's see if it doesn't really matter. Is it right? Derived tensor, Shanjian? Okay. All right. So therefore, this one will correspond to this Tame Springer shift tensor with over this group algebra. And if L divides Q minus 1, if L does not divide Q minus 1, it's good situation. But if it divides, then this, okay, so this is, recall this is inside inco log 10, and then further inside the inco of everything without adding the unipotent singular support condition. And inside here, this is a copy of a coherent sheaf. Okay? And then the point is this one is not in the coherent sheaf. It's not in co. Okay? So it's not a compact object, and it really does not inside there. So this is actually bad because, like the Iwahori like compact induction from Iwahori subgroup could be such important object, and it doesn't correspond to anything in the category of coherent shift. So actually, there's some. So I would say suggest a better way to do for modular coefficient. Actually, I think better formulation of categorical local Langlands is we do slightly different version. So definition, I'll take a sheaf, I so-called the finite generated ISOC, to be those F inside the all sheaves such that I B upper shrink of F is finitely generated as a representation of GQP, and and is 0 for almost all B. So these are like, if it's in the case of characteristic 0, these are the same as compact objects. But in positive characteristic FL coefficient, it's a non-binary situation. The typical example is just this one. This is a finite generated. It's generated by one, but it's not a compact object. And the conjecture is, at least for not too small prime L, is this guy should be just the equivalent to all category of coherent sheaf on log cis. So without adding the singular support condition. And what's going on here, we are seeing this compact object, this, and in this case, actually this compact induction of Iwahori, this will correspond to this coherent Springer sheaf S1 introduced by in Davis' talk. And what's really going on here? Here I'm saying this guy is not in co, and then here I say this one is supposed to be in co, is in category of coherent sheaf. And what's really going on is in this category there's another copy of a coherent sheaf inside here. And what happens is this guy sits inside this copy, but not sits inside this one. And this is two copy of coherent sheaf. I heard different discussions before, and this is actually give you a really concrete example is what's even just for the Iwahori algebra is going on. All right, so I'll stop here.